Good day, we are Group 4, and today we will be discussing about dynamic programming. First, the team members. Group 4 is composed of Christian Olandria, yours truly, Lindy Mandawe, Jayrald Bernales, Kimberly Ligan, Ann Ocmar, and Laurence Reyes. Next, the overview of our report. Our topic is mainly focusing on dynamic programming and the following scopes. First, we have introduction to dynamic programming and its relation to recursion. Next, we have dynamic programming characteristics, approaches of dynamic programming, solving common dynamic programming algorithms, advantages of dynamic programming, and also dynamic programming applications. So, what is dynamic programming?
Good day everyone, I am Ann Ocmar, and in this video presentation, our group will going to tackle about the dynamic programming and its relation to recursion, the overlapping subproblems and optimal substructure, and solving the common dynamic programming problems such as Fibonacci sequence, longest common subsequence, and knapsack. So what is dynamic programming and its relation to recursion? Dynamic programming is a mathematical and computer science technique for solving big problems by breaking them down into smaller subproblems. It avoids duplicate computations by solving each subproblem once and saving the answers, resulting in more efficient solutions for a variety of issues. The relation between recursion and dynamic programming lies in how they approach problem solving. Recursion solves problem by breaking a difficulty down into smaller problems of the same problem. A function calls itself to solve the problem until a specific condition is met. While the dynamic programming improves on recursion by storing the results of subproblems and avoiding redundant calculations. In essence, dynamic programming is recursion with optimization through memory.
Dynamic programming is a strategic approach used to solve complex problems by breaking them down into simpler, manageable subproblems. It is particularly effective for optimization problems and relies on two fundamental characteristics such as overlapping subproblems and optimal substructure. In overlapping subproblems means that the problem can be broken down into smaller subproblems where the solutions to the subproblems are overlapping. Having subproblems that are overlapping means that the solution to one subproblem is part of the solution to another subproblem. It refers to the scenario where a problem can be divided into smaller subproblems that are solved multiple times throughout the process. For instance, when calculating Fibonacci numbers, the same values like Fibonacci 3 or Fibonacci 2 are computed up repeatedly. If we use a naive recursive approach, dynamic programming addresses this inefficiency by storing the results of these subproblems, allowing us to reuse them instead of recalculating. Example, in the Fibonacci sequence, to calculate Fibonacci 5, you need Fibonacci 4 and Fibonacci 3. But to calculate Fibonacci 4, you again need Fibonacci 3 and Fibonacci 2, where Fibonacci 3 is computed multiple times. By storing its value after the first calculation, we can save time and resources. In optimal substructure, a given problem is said to have optimal substructure property if the optimal solution of the given problem can be obtained by using the optimal solution to its subproblems instead of trying every possible way to solve the subproblems. It means that the complete solution to a problem can be constructed from the solutions of its smaller subproblems, so not only must the problem have overlapping subproblems, the substructure must also be optimal so that there is a way to piece the solutions to the subproblems together to form the complete solution. It means that the optimal solution to a problem can be constructed from the optimal solution of its smaller subproblems. This implies that if we can solve the smaller components optimally, we can combine the solutions to form the best overall solution. For example, consider the shortest path problem in a graph. is if you want to find the shortest path from point A to point C via point B, the shortest path from A to B and from B to C must also be the shortest path. Thus, by ensuring each segment is optimal, we can guarantee that the entire path is optimal as well. There are also two approaches in dynamic programming, such as top-down approach and the bottom-up approach. In the top-down approach, it is also known as memoization. We can start with the final solution and recursively break it down into smaller sub-problems. To avoid redundant calculations, we store the results of solved sub-problems in a memoization table. Let's break down the top-down approach. Starts with the final solution and recursively breaks it down into smaller sub-problems. Stores the solutions to sub-problems in a table to avoid redundant calculations. Suitable when the number of sub-problems is large and many of them are reused. For example, Fibonacci series calculation using memoization. In bottom-up approach, it is also known as tabulation. We can start with the smallest sub-problems and gradually build up to the final solution. We store the results of solved sub-problems in a table to avoid redundant calculations. Let's also break down the bottom-up approach. First, starts with the smallest sub-problems and gradually builds up to the final solution. Second, fills a table with solutions to sub-problems in a bottom-up manner. Third, suitable when the number of sub-problems is small and the optimal solution can be directly computed from the solutions to smaller sub-problems. For example, longest common subsequence or the LCS calculation using tabulation.
Good day everyone. So in a part we'll be discussing the common algorithms that uses dynamic programming. Gi-categorize nila mo into 3 levels, easy, medium, and hard. So as per sa ako ana part, I'll be discussing the easy level, which is ang Fibonacci sequence and longest common subsequence. So let's start. Imagine you're baking a cake. You have a recipe, but it's a bit messy. You keep making the same parts of the cake over and over, wasting time and ingredients. So here comes dynamic programming. Dynamic programming is like cleaning up that recipe. It's a way to solve problems by breaking them into smaller parts, how to make each part. Example, sa Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones. The Fibonacci sequence is like a recipe for numbers. Each number is the sum of the two previous ones. 0, 1, 1, 2, 3, 5, 8, and so on. So, kung gamitan na to siya og brute force, this is like making the sequence step by step, adding the same numbers over and over. For example, kung pangitaon na to ang ikalima na Fibonacci number, you need to calculate the fourth and third, which is in turn require you to calculate the second, first, and so on. Like, you're essentially baking the same cake parts multiple times, magbalik-balik ka. This approach repeatedly calculates the same Fibonacci numbers, leading to inefficiency, especially for larger values of numbers. Whereas, kung gamitan na to siya og dynamic programming, you write down the first few numbers, tahay 0 and 1, and then use those to calculate the rest. You only calculate each number once and store it for the future use. Like, you only bake each part once, saving time and effort. This approach stores the calculated Fibonacci numbers in an array, avoiding redundant calculations and improving efficiency. This is the code example for Fibonacci sequence. Given a positive integer n, the task is to find the nth Fibonacci number. The Fibonacci sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. For example, I have an input n equals 2. The output is 1. The explanation is 1 is the second number of Fibonacci series. Another example, if I have n equals 5, the output is 5. The explanation states that 5 is the fifth number of Fibonacci series. So, in that case, we use naive approach using recursion. We can use recursion to solve this problem because any Fibonacci number n depends on the previous two Fibonacci numbers. Therefore, this approach repeatedly breaks down the problem until it reaches the base cases. It is straightforward but inefficient. Same ani nga code example. Here, how it works. The first line, the function is called int Fibonacci and takes a number n. This function calculates the nth Fibonacci number using recursion. This function takes an integer n as an input and aims to return the nth Fibonacci number. The second line, base case, if n is less than or equal to 1, then return the value of n. This handles the starting numbers of the sequence. If n is 0 or 1, the function simply returns n. The third line is the recursive case. Return int Fibonacci n-1 plus n Fibonacci n-2. This is the core of the recursion. To find the int Fibonacci number, the function calls itself twice. Once to calculate the n-1 Fibonacci number and once for the n-2 Fibonacci number. It then adds these two results together to get the nth Fibonacci number. Example, let's say you want to find the fourth Fibonacci number, n equals 4. First, the nth Fibonacci 4 calls n Fibonacci 3 and n Fibonacci 2. Step 2, n Fibonacci 3 calls n Fibonacci 2 and n Fibonacci 1. Third step, n Fibonacci 2 calls n Fibonacci 1 and Fibonacci 0. Both n Fibonacci 1 and n Fibonacci 0 return their respective values 0 and 1. These results are then added up, working their way back up the recursion tree. This recursive approach is inefficient because it calculates the same Fibonacci numbers multiple times. For example, to find the fifth Fibonacci number, it calculates the third Fibonacci number twice, once when calculating the fourth number and again when calculating the fifth number. As n gets larger, this redundancy becomes increasingly problematic. So, mo nang gagamit ta og expected approach mo ang memorization approach. Though, ang katong naive approach is okay man sab siya, pero inefficient lagi man ang mogamit ta og lain nga approach. In the previous approach, there are a lot of redundant calculations that are calculated again and again. So, we can store the results of previously computed Fibonacci numbers in a memo table to avoid redundant calculations. This will make sure that each Fibonacci number is only computed once. This will reduce the exponential time complexity of the naive approach into a more efficient time complexity. Memorization is a technique that involves storing the results of expensive function calls in a table called a memo table to avoid recalculating them. Same ani nga code example. Here's how it works. Sa first line, a function in Fibonacci that takes an integer called n and an array called memo as input and returns an integer. This is a helper function that does the actual recursive calculation, but it also uses a memo table. The line n memo n plus 1. A memo table is created with a size of n plus 1 to store the calculated Fibonacci numbers. It is initialized with -1, indicating that the Fibonacci numbers haven't been calculated yet. So, ano ito sa line sa memorization check? If the value of at index n in the memo array is not equal to 1, then return the value at the index. Before calculating a Fibonacci number, this code checks if it is already stored in the memo table. If it is, the function returns the value directly, avoiding redundant calculations. The sunod na line, the recursive calculation and memorization. Calculate the value of nth Fibonacci util with n minus 1 plus the value of nth Fibonacci util with n minus 2 and store the result in the memo array at index n. Then return the value at index n. If the Fibonacci number isn't in the memo table, it's calculated recursively, and the result is then restored in the memo table for future use. Example, imagine calculating the fifth Fibonacci number. First step is nth Fibonacci util 5 memo is called. Since memo 5 is minus 1, it's not yet calculated. Next step is nth Fibonacci util 4 memo is called. Then nth Fibonacci util 3 memo is called. Then nth Fibonacci util 2 memo is called. Nth Fibonacci util 1 memo is called and returns 1. Nth Fibonacci util 0 memo is called and returns 0. Now, nth Fibonacci util 2 memo can be calculated using the values from steps 6 and 7 and stored in memo 2. Similarly, nth Fibonacci util 3 memo and nth Fibonacci util 4 memo can be calculated and stored. Finally, nth Fibonacci util 5 memo is calculated using the values from memo 4 and memo 3. This approach avoids the repeated calculations that plague the naive recursive approach. Memoization is a powerful technique for optimizing recursive functions by storing and reusing previously calculated results. It significantly improves the time complexity while maintaining the structure of the recursive solution. Ikaduha is ang longest common subsequence or ang LCS. The longest common subsequence or LCS problem involves finding the longest subsequence that is common to two given sequences. Finding the longest common subsequence is like finding the longest matching ingredient list between two recipes. Kung gamitan na to siya og naive approach, you try all possible combinations of ingredients which can take a long time. This approach explores all possible subsequences, leading to exponential time complexity, making it inefficient for longer strings. Whereas kung gamitan siya nato og dynamic programming, you break down the recipes into smaller ingredient lists and compare them. You remember the longest matching list and use them to build up the final answer. For tahay, aning laing example, na ako input S1 is ABC and S2 is ACD. The output is 2. Ang explanation ani is the longest subsequence which is present in both strings is A and C. Mao na siyang output is 2. Ani nga sample, kung gamitan nato siya og dynamic programming approach, is like having a smart way to organize your search. Like, you create a table with ABC at the top and ACD on the side. Each cell in the table represents the longest matching string between the corresponding parts of the words. The cell at A and A is 0 because the empty parts of A and A share no letters. The cell at C and C is 1 because C is shared between ABC and ACD. The cell at D and C is 1 because C is shared between ACD and ABC. Pero kung gigamitan nato siya og naive approach, very time consuming siya, especially if the words are long. Kay it's like trying every possible combination of letters from each word. You compare each combination one by one to see if they match, and you keep track of the longest matching string you find.
Here's a sample code of the longest common subsequence using the Java language. The LCS function, this function takes two strings, the S1 and S2, and two integers, the M and N, which represents the lengths of these strings. It recursively calculates the length of their longest common subsequence. So, here's how it works. If the length of either strings becomes 0, the longest common subsequence is 0 because there are no characters left to compare. If the last character of both strings is the same, it means this character is part of the longest common subsequence. So, we add 1 to the longest common subsequence length and move to the previous character in both strings. If the last character of S1 and S2 are different, the LCS could either exclude the last character of S1 or exclude the last character of S2. The function computes both possibilities and returns the maximum value of the two. This ensures that we find the longest common subsequence. So in the main function, there are two strings, the S1, which has the string of AGGTAB, and the S2, which has the string of GXTXAYB. The length of both strings are stored in variables m and n. Then the LCS length is calculated by calling the LCS function with the strings and their length as arguments. And when you run this program, it will print the length of the LCS of these two strings. Then the length of the LCS is 4, which is the GTAB.
The 0-1 knapsack problem. The 0-1 knapsack problem is a type of knapsack solved using a dynamic programming approach. It can be defined as follows. We are given n items where each item has some weight, Wi, and value Vi associated with it. We are also given a bag with capacity W. The target is to put the items into the bag so that the sum of values associated with them is the maximum possible. So, the knapsack problem is a classic example of dynamic programming used to maximize profit while staying within a given weight limit. A simple solution is to consider all subsets of items and calculate the weight and profit of all subsets. Consider the only subsets whose total weight is smaller than W. Pick the subset with the maximum profit of all such subsets. You are given n items where each item has a weight or Wi and a value or Vi. You also have a bag with a maximum capacity of W. Your goal is to put a combination of items into the bag so that the total value of the items inside the bag is as large as possible without exceeding the capacity of W. So for example, imagine nagdakaw bag with a limit nga yung W is tang to 20. Og na kay mga butang nga bugat, og na kay mga ang value sa imong butang is butang na to mga 8. Gusto nimo ibutang sa bag ang mga butang nga dili malapas sa kapasidad aron makuha nimo ang pinakadako nga total value. In brute force solution, ang pinakasimple nga solution sa problema mao ang pagtan-aw sa tanan nga subset sa mga items. Para ani nga approach, imong i-calculate ang total nga bugat o value para sa matag subset. Like for example, kung nakay upat ka butang, imong tanang combinations. Ang una is Y butang. Ang ikaduha is ang una lang ang ibutang nya. Ang ikatulo is ang katong duha ka butang. Ya mo to ikaupat, katong tulo ka butang, ya hangtod sa upat ka butang. Karon imong i-filter ang mga subsets nga dili malapas sa capacity sa bag. Ug ang pinakadako nga value gikan sa kanila ang imong solusyon. However, this approach is not efficient. Kung daghan na kayo ang items, taas kayo ang oras sa pagtan-aw sa tanan nga combinations. That's why we use dynamic programming. Schema structure. In dynamic programming, at each step, you decide whether to include an item in the bag or not. The solution for the larger problem can be constructed using solutions to smaller subproblems. For every item, nakay duha ka cases. Ang case 1 is ibutang nimo ang butang sa bag. Like for example, kung imong idugang ang butang, kinahanglan nimo ibutang ang weight sa bag and ang value nga naa sa butang. And the case 2 is dili nimo ibutang ang butang sa bag. Example, kung dili nimo idugang ang butang, then imo lang i-consider ang mga value sa mga existing items. By breaking down the problem, dynamic programming can efficiently find the optimal solution by solving smaller problems and combining their results. Here is an example of a recursion tree. Top-down dynamic programming approach. The code uses a top-down dynamic programming approach, which involves breaking down the problem into smaller sub-problems, solving each sub-problem only once, and storing the results in a table for future reference. Knapsack recursive method. This method is the recursive function that solves the 0-1 knapsack problem using dynamic programming. It takes 5 parameters. W is the capacity of the knapsack. WT, the weights of the items. Val, the values of the items. And the number of items. And DP, the table to store the results of subproblems. The base cases are when n is 0 or w is 0, in which case the method returns 0. If the result of the current subproblem is already stored the DP table, the method returns the stored value. If the weight of the current item is greater than the capacity of the knapsack, the method returns the result of the subproblem without including the current item. Otherwise, the method returns the maximum value between including the current item and excluding the current item. Knapsack method. This method is the main function that initializes the DP table and calls the knapsack recursive method to solve the 0-1 knapsack problem. It takes 4 parameters. W is the capacity of the knapsack. WT, the weights of the items. The VAL or val, the values of the items. And N, the number of items. This method initializes the DP table with -1 and calls the knapsack recursive method to save the problem. Driver code. The driver code creates an instance of the GFG class and calls the knapsack method to save the 0-1 knapsack problem with a capacity of 50 and 3 items with weights and values. For the given input, the output will be 220. This approach promotes time complexity. The time complexity of top-down dynamic programming approach is 0, where n is the number of items and w is the capacity of knapsack. Space complexity. The space complexity of the top-down dynamic program approach is 0, where n is the number of items and w is the capacity of the knapsack.
Good day, this is Olandria, and I will be discussing about palindrome partitioning. In the English concept, a palindrome is a word that if you reverse that word, it is still the same. We have examples like wow, madam, level, kayak, and many more. In this specific discussion, I will discuss about palindrome partitioning. First, we have its definition. Given a string str, a partitioning of the string is a palindrome partitioning if every substring of the partition is a palindrome. The task is to find the minimum number of cuts needed for palindrome partitioning of the given string. If a specific string is already a palindrome, there is no need to make some cuts as it is already considered a palindrome. So it will only return 0 cuts. In the example, as you can see in the example, you see some palindrome partitioning where it made 3 cuts. For more examples, I'll give you some. If the input string is geek, G-E-E-K, we need to make some considerations. First, we have G, then we make some cut, and then EE, which is considered a palindrome, then we have another cut and separate k. In that specific example, we make 2 minimum cuts. If the input string is AAAA, it is already considered a palindrome, so there is no need to make some cuts. So the output would be 0 cuts. And then if the input string is ABCDE, we have A, then make some cut, B, another cut, C, D, another cut, and E. In that specific example, we have 4, or we make 4 minimum cuts. And lastly, the input string is ABBAC. We have a palindrome which is ABBA. And with that, we make 1 cut and separate C. So in that specific example, we make 1 cut. Next is the recursive approach. A recursive approach is the naive approach to solving the palindrome partitioning problem. In this approach, we will try to apply all possible partitions and return the correct combination of partitions at the end. In this approach, we recursively evaluate the following conditions. If the current string is already a palindrome, then we simply return true. Otherwise, we try to make some cuts at all possible places, recursively calculating the cost for each cut and return the minimum value. If we consider the recursive approach, it has overlapping subproblems that leads to redundant computations, thereby resulting in exponential time complexity, making it more time-consuming. This redundant computation can be achieved by solving using dynamic programming approach. The problem can be solved by finding the suffix, which is the palindrome partitioning, starting from j and ending at index I, which are palindromes. Hence, we make a cut here that requires 1 plus min cut from res substring. For all such palindromic suffixes starting at j and ending at index I, keep minimizing in mincut dp. Similarly, we need to compute results for all such I. And finally, the mincut dp will be the minimum number of cuts needed for the palindrome partitioning of the given string. To make it more understandable, we consider some 2 requirements in the dynamic programming approach of palindrome partitioning. First, we check both ends, the beginning character and the end character of a specific string. If those 2 are equal or it match each other, then we proceed to the next condition that will check the inside palindromes, the inside characters, if that inside characters is a palindrome. For example, wow, we check both ends and we can see that both ends, the beginning and the end, are W. So we proceed with the second step and check if it is a palindrome. And then the inside character is, the inside substring or character is O, and then it is a palindrome, so it is considered a palindrome. So here is a code implementation for dynamic programming approach. As we can see, it is quite difficult to understand with these specific functions or methods and code blocks. So we will make some breakdown to understand this. First, the generating palindromic substrings. If we can see, there is a method called static boolean generate palindrome. And that specific method initializes a 2D boolean array, which is inside the boolean pal. This boolean pal will track whether substrings of S are palindromic. First, it will mark all single character substring as palindrome. Then, as I stated with the requirement earlier, the 2 necessary requirements, it checks for substrings of increasing lengths and mark them as palindromic if the characters at the ends are equal and the inner substring is also a palindrome. Next, the min-cut method. Static int min-cut string s. This min-cut method calculates the minimum cuts required to make all substrings of s palindromic. It initializes a min-cut dp array. You can see it, the min-cut dp array, that will store the minimum cuts needed for substrings from start to each position in S. If the substring from the start to I is palindrome, no cuts are needed. Otherwise, it will check all possible cuts and update the minimum cuts required. And lastly, the main method will initialize a string and calls min-cut method to print the result. With this dynamic programming approach promotes time complexity and space complexity. With time complexity, the algorithm runs in big O n to the power of 2 time due to the nested loops for checking palindromic substrings and calculating minimum cuts. With space complexity, the space complexity will make things easier because of the 2D array used to store palindrome information.
Good day, sir. My name is Jayrald Bernales, and I'll be talking about the advantages and applications of dynamic programming. Advantages of dynamic programming. Dynamic programming offers several benefits. First is it's time efficient. It avoids recomputing the same subproblems multiple times, saving significant time. Second, it offers optimal solutions. It finds the best solution by considering all possible combinations. And lastly, problem simplification. It breaks complex problems into smaller and manageable subproblems. Applications of dynamic programming. Dynamic programming is used in various fields. First is optimization. It solves problems like the knapsack problem, shortest path problem, and the maximum subarray problem. Second is computer science. Useful for tasks like longest common subsequence, edit distance, and string matching. And lastly, operations research. It helps with inventory management, scheduling, and resource allocation. In conclusion, dynamic programming is a method used in mathematics and computer science to solve complex problems by breaking them down into smaller subproblems. Dynamic programming is an optimization technique used when solving problems that consist of the following characteristics: optimal substructure and overlapping subproblems. Optimal substructure means that we combine the optimal results of subproblems to achieve the optimal result of the bigger problem, while the overlapping subproblems means that they can be divided into smaller subproblems with overlapping solutions.